Hello. This one's going to be kind of a spiritual sequel to my video about constructors, where, among other things, I argued that the design of constructors in C++ makes it easy to accidentally view your program in an invalid state. And I compared it to the approach taken in Rust, which is much simpler and neatly solves all the problems I brought up. In this video, we're going to do a very similar thing with move semantics in C++, where I'll argue that the details of how they're designed in C++ lead to your code having weaker invariants, worse performance than ideal, and more complexity. I'll compare it to the approach to moves that Rust takes, and once again, I'll argue that Rust's simpler approach also just makes everything better. Now, this might sound like I'm just being overly negative here about C++, so keep in mind, I like C++, I like move semantics, and this is all just a thinly veiled excuse to talk about cool stuff in a bunch of detail. So you hear a lot about invariants. I like talking about them. In this discussion, we'll take a bit of a lower level perspective on them. So recall that your computer's memory is made out of nothing more than ones and zeros. Those ones and zeros have no inherent meaning whatsoever. It's literally just the physical state that some silicon happens to be in. Now, your processor allows you to talk about those ones and zeros in groups of 8 called bytes. And your computer's memory, the physical address space, is just an incredibly large two-dimensional array of those bytes. I say two-dimensional because on the horizontal axis, we have the memory addresses of each byte. And then at each address, there's sort of a depth of 8 because there are 8 bits we can talk about located at that address. Now, once again, this memory is meaningless. It's formless and void. It's a blank canvas for us to paint meaning onto. We do that with our programming languages. Our programming languages talk about this memory at a slightly higher level. They give us tools called types for carving it up into meaningful chunks. For example, when you declare an unsigned 32-bit integer, your programming language creates a sort of facade overlaid on top of 4 of those meaningless bytes and says, okay, while this integer exists, these 4 bytes are going to be meaningfully linked together, and they're going to work together to represent all the different binary digits of this single logical integer. Your programming language coordinates that and lets you believe there really is an integer there, but there's not, at least in your CPU's eyes. And by the time the compiler has finished and your program is running, the facade is gone, and your program is just doing 4-byte integer operations that the compiler generated on a piece of raw, meaningless memory. This is one ability of types to be able to describe the shape and size of the pieces of data we'll be working on. For example, with a struct, we can talk about a larger chunk of memory that has multiple primitive pieces of data in it. But just knowing what memory we're allowed to talk about doesn't help us know how that memory should be used correctly within the larger context of our program. That's where invariants step in. So invariants are when there are patterns of ones and zeros that you could write into the memory you have allocated for your type, but that you won't because they describe a state that is illegal. As an example, let's picture a dynamic array like std vector from C++. This vector of t has 3 fields, and each one has an invariant. The pointer describes where the buffer we have allocated is located. The len says how many chunks of memory at the start of that buffer have had t's constructor run on them, and then the cap is the total size of that buffer. So clearly we can't just write any ones and zeros into these fields. The ones and zeros we write have to reflect the truth of what has happened up until now with this vector. It's the job of the vector's implementation to protect these invariants at the level of the programming language and enforce that any modifications to its fields still result in a valid state. This vector on screen is clearly empty. It has no allocated buffer, no constructed elements, no capacity. Now, it is physically possible for us to go in there and write a different value to the memory that underlies this integer field. But I hope that you can see how that could cause serious problems for us. Our vector would start reporting the wrong size, and depending on the exact implementation, we could easily start dereferencing null pointers or whatever else. So we've corrupted this vector by breaking its invariants, and we've completely lost the ability to trust that it will behave as we want it to. And that's the crux of it. Invariants are vital. Invariants are the structural unit of being able to reason about what your code does whatsoever. Your computer's memory, without invariants placed upon it by your code, might as well be filled with random ones and zeros, at which point we might as well have never written any code at all, because that's also how it already was before we started. That's obviously taking things to the extreme, but it is a sliding scale. Weak invariants lead to difficulty reasoning about your code and suboptimal performance because both you and the compiler's optimizer have to spend more time checking for edge cases. Strong invariants simplify your logic and increase your code's robustness, and corner cases don't have to be accounted for because they don't exist. I'm going to show you a simple example of that. But first, I feel bad moving on from this section without pointing out that you should strive to reduce the number of illegal bit representations that your type has. You'll often hear people saying it this way. I literally could not possibly agree with this sentiment more, but it's a little out of scope for this video. Let's talk about it another time soon. Okay, example of strengthening invariants. So C++ has two ways to refer to an object that you know is sitting at a particular place in memory. There's the pointer on the left and the reference on the right. Now, these two language features are pretty similar, although the type of gray hairs each one adds to your head is actually a little different. But they're both represented in memory as a 64-bit memory address, assuming, of course, you're on 64-bit. But one very salient difference is that pointers can be null, and it's well supported. There's even a special language keyword that denotes a unit value that can implicitly convert to a null pointer of any type. References, on the other hand, can't be null. Same representation as a pointer in memory, but they add the invariant that the bit pattern of all zeros is illegal. And I can already hear that person typing that comment saying, you actually can have a reference to null, to which I say, no, you actually can't have a reference to null. Any attempt to create a reference to null boils down to something like this. You have to create a null pointer and then dereference it to turn it into a reference. That means you are dereferencing null, and you can't do that. It's undefined behavior to dereference null, so by doing this, all bets are off and you can no longer reason about your code anyway. It's as bad as scribbling random bits all over the length field of our vector. Now, do I wish C++ made it a little harder to do something so bad? Definitely. But this invariant is ironclad in the language, and it gives us power over a pointer's weaker invariant. Let's say you have a public API that needs to refer to some object to do its work. I'm purposefully using the word object for this type because there are a lot of types, especially if you're working in a more object-oriented way, that you're just kind of used to passing around by pointer. But that means that the first thing you need to do in this public API is probably check for null. Maybe if we get a null, we just want to early out or otherwise fail in some way. Now, inside the happy path, you're going to pass the object along to some helper functions that help you carry out your actual logic. So what do these helper functions look like? Well, you might write them like this. They take the object by pointer and do whatever they do. But should they null check? I mean, we already null checked at the call site. It's wasteful to do it again. But having to know what the call site looks like while we're looking at these functions breaks the local reasoning and the encapsulation that's the whole point of using a function. And what if we add another call site later and that call site expects us to check for null inside the helpers? So we should check for null, right? That means in order to get safety and local reasoning for each function in isolation, we need a linear number of null checks throughout our call hierarchy. Also, what do we do if the null check fails? Especially this top one, we're expected to return a value. Maybe there's a good default value to return, maybe there's not. Now, pausing here. I've been in code reviews where I've brought this kind of thing up, and people are like, this is paranoia. I know what I'm doing. I know the object is not null. And it's like, maybe you know that, but everyone would know that if you say that in your code. One way is to assert or something, but a much better way is to use a type that cannot represent null as one of its possible values. You have to type either an asterisk or an ampersand, so choose an ampersand. With a stronger invariant, it says much more about the code you're looking at, both inside and outside the function. The question of whether it's null? No, it's not. We peeled off that layer of uncertainty already at the top level of our API, and now our implementation gets to forge ahead with strong guarantees about what it's doing and code that inspires confidence instead of doubt. For a comparison, let's see how Rust handles nullable references. In Rust, references are sort of a middle ground between C++ references and C++ pointers, with the major added feature that the borrow checker tracks them to. But one similarity they have with C++ references is that they can't be null. For a nullable reference, you could do this and use a raw pointer, but that is not how you should do it. The right way to do it is with an optional reference. And this is very elegant if you ask me. We have a non-null reference, and using option, we add one more possible state to it, which is none. But surely this adds some overhead? I mean, option is like a discriminated union, and it needs somewhere to store whether it's some or none. Well, it has one. Of all the possible values of the memory underlying a reference, our non-null invariant for references means this one is illegal. The Rust compiler knows that, and so it takes advantage of that automatically. It uses all zeros to mean none and anything else to mean some reference. That means we get a nullable reference with zero space overhead and with the full nice API of option, which makes it really hard to forget to null check. And then once we do null check, we unwrap the reference from the option, and everyone further along in our call hierarchy doesn't have to check anything. C++ could do this with optional references. It's not built into the compiler like it is in Rust, but the standard library could definitely implement it with template specialization. For reasons I don't really understand, they don't do that. In fact, they just make this a hard error. It's too bad. Also, it's not just references that could benefit from these kinds of niche optimizations, as Rust calls them. Really, any type with any invalid bit representations could, in theory, repurpose those and let optional use them for the empty state. But we don't have this with standard optional. To be fair, Rust doesn't have a fully general mechanism for this either, although there's work being done in that space. Oh yeah, this video is supposed to be about moves. Okay, so one of the things that you sometimes have to do when you have these values overlaid on your computer's memory is that sometimes you have to take them from the memory location where they are and put them at a different one. Maybe you're passing them into a function and the calling convention expects them at a certain place in memory. Or maybe you're calling sort on an array, which fundamentally is about changing where in the array the values are. So your CPU can do this natively. It has dedicated instructions for taking some data that's stored here and putting it there instead. Funnily enough, these instructions are usually called move, even though they copy data from one place to another. This is for copying around smaller data, generally like the size of registers. The C standard library provides a function called memcopy for copying larger chunks of memory like big structs or arrays. And this is the end of the conversation for types like integers, where the entire semantics of the value is present inside of its shallow bit representation. All you have to do is copy those bits somewhere else, and then you have a new integer that's just as good as the old one. But the thing is, oftentimes our bit representations describe some external state that needs to be maintained when we copy our bits around. For example, imagine an owning pointer. The invariant of this data is that the address stored here actually points to some memory we've allocated and that we are responsible for freeing when we're done. If we try to take this and put it somewhere else, we need to establish that exact same invariant in the new location. One way is to create a new allocation and point at that from the new location. This is actually what C++ tends to do by default. If you write the simplest C++ syntax, you are probably doing deep copies like this when you pass around values that own allocations. I hope you can see why this is undesirable. It's exorbitant to allocate memory just to shift a value around. The smarter thing to do is to use the existing memory we already have allocated and just copy the pointer to it. That's a million times faster. But there's a problem here. Now we have two pointers pointing at the same memory, and both of them think it's their job to deallocate it when they're done with it. But a lot of times, you are transferring the value to a new location, and after that, you don't need the old value anymore. You only need it in the new location. So if that's the case, what can we do with that old value to prevent this double free problem? Well, Rust and C++ have different answers to this question. Rust forgets that the old value ever existed. It doesn't run a destructor, and it doesn't let you talk about the old value anymore. It is gone. This is how Rust implements move semantics. It memcopies the shallow bit representation of the value to the new location, and then just never thinks about the old location ever again. You'll hear this called a destructive move. By moving out of the old value, we implicitly destroyed it. So we don't need to explicitly call its destructor, let alone allow you to refer to it after it's been destroyed. C++ has a different story. C++, the language, actually doesn't do much here. It keeps the old object alive after it's moved from, and it leaves it up to the author of the type as to what exactly to do. For an owning pointer like this, what would probably happen is the implementation would break the link between the pointer and the allocation by setting the pointer to null. Now, when the object is destroyed and its destructor runs, there's no allocation for it to free, so its destructor doesn't do anything. But notice that we just weakened our invariant. I didn't say anything about null before. I said this pointer owns an allocation. But in order to move from it in C++, we have to say, well, it can also be null. And so we've lost some of the simplicity and strength of this type. And remember, I also mentioned that when we destroy this empty value, a destructor is going to end up running that does nothing. The compiler might be able to see that and optimize it away, but there are plenty of cases where the compiler can't, so it still has to call destructors for moved from objects that end up just being a waste of time. Now, it's important to note that C++ didn't have move semantics at first, and so when it was introduced, it had to be introduced in a way that didn't break anything. That's a big part of why it looks the kind of strange way it does today. In fact, I think you could make a strong argument that C++, the language, doesn't have move semantics at all. It has two separate language features that conspire together to let library authors implement move semantics. There's function overloading, and then the real special sauce, there's a new type of reference introduced in C++ 11 that is used for objects that are probably fine to move from. Let's look at how those references work. So, the thing that sets the different kinds of references apart in C++ is what sorts of objects each one is allowed to refer to. We say a reference binds to a given object, and then it refers to that object forever. This kind of reference, for example, this non-const reference with only one ampersand, can only bind to values like this. It can bind to variable names directly or to sub-objects that are reachable through variable names. These are called L values, and they pretty much correspond to any expression that you're allowed to take the address of. Another way to think of it is any single object that you could refer to multiple times in your code by copy-pasting the expression that refers to it. So these are L values, and this type of reference with one ampersand is called an L value reference. Notice again, there's no const, so there's the added constraint that this reference can only bind to these expressions if they evaluate to an object that's not const. Now, in C++ 11, in order to power move semantics, they introduced a brand new type of reference. This reference cannot refer to L values, it won't compile, but it can refer to expressions like this. It can refer to expressions that evaluate to a brand new object, or the address returned by the address of expression, or a function call expression if that function returns by value. Notice that you are not allowed to take the address of any of these. And copy-pasting these expressions would actually evaluate to brand new values a second time, not the same values as the first time you type them. So these are called PR values, which is supposed to sort of be short for pure values in some platonic sense. They don't have an address yet. They're just kind of these idealized values floating in the ether in your code. A double ampersand reference is one way to grab hold of one so you can use it. So that's PR values. Now, I already mentioned that these references cannot be used with L values. And that's true, at least implicitly. But you can actually explicitly cast an L value expression to a double ampersand reference. When you do this, you create what's called an X value, which is short for an expiring L value, because it's like we're taking what was once an L value and casting it into the ether. Now, if you've studied move semantics before, you know that the standard library provides a special function for doing this cast, and it's called move. But when you call move, all you're doing is nudging an L value to become an X value. C++ refers to these collectively as R values. So an R value is either a PR value or an X value. And this double ampersand reference is called an R value reference. By the way, to finish the story, you might also hear the term GL value, and that just refers to an L value or an X value. So these are all the value categories in C++. There are a couple more types of references, though. By the way, I'll tell you right now, we're skipping forwarding references, so don't come at me. We'll talk about those some other time. The next kind of reference I do want to talk about is the const L value reference. If you have a const L value reference, the rules are slightly different from a non-const L value reference. Const L value references can refer to anything at all, both L values and R values, const and non-const. The const means it can bind to any L value, whether const or not, since it's always safe to add const. And the const also makes it safe to bind to R values, whereas binding a temporary to a non-const L value reference would be a major source of bugs, so it's prohibited. So const L value references are very useful, especially for function parameters that you just need to look at. Lastly, there are const R value references. These can only refer to R values. You need to be aware of these if you're writing super generic library code, but const R-value references aren't useful for anything. Because as we're about to see, to get the most out of R-value references, you need them to be non-const. And if they are const, you should just use const L-value references since they already work for everything. So we're just going to ignore const R-value references. Actually, we're just going to focus on these two. The trick here that gives us move semantics is that you can overload functions based on these reference types. Here I have two overloads of the function f. If I declare an s and then call f with an L value, just s's name, it will call the overload that takes a const L value reference. Remember, it can't call the R value reference one because R value references can't bind to L values. So overload resolution picks the const ref overload. But if I call f with a PR value or an X value, it will call the R value reference overload. It could call the L value reference overload since const L value references can bind to R values, but the R value reference overload is a better match according to the overload resolution rules, so that one wins. So having these two ways of passing parameters actually ends up calling two different functions. And move semantics is when I do different things in those two functions. More on that in a second. I want to point out real quick that if I remove this R value reference overload, the code still compiles. It's just that the R value cases fall back to the const ref overload. This is kind of cool. If you have a const ref overload of your function, you can always add or remove an R value reference overload without breaking your code. This is how move semantics got into C++ at all in a backwards compatible way. You can start adopting move semantics by starting to sprinkle around R value reference overloads, but your code still works whether you do or not. So what does this have to do with moving, though? Well, we can overload functions based on reference types, and one of the kinds of functions we can overload is constructors. So let's say we have a class with an expensive resource in it. If we want to be able to copy this class, we need to have a constructor that takes in an existing instance of our class and creates a new one from that. This is called a copy constructor, and we take the existing instance by const L value reference. So right now this works for any possible source object. We'll make a copy of the expensive resource and use that for our instance. But this is an expensive resource. What if we added an overload of this constructor that took an R value reference? What we know about R values is that they're either temporary expressions or L values that have been explicitly cast to look like temporary expressions. In other words, we have a strong reason to believe that they're going to be destroyed very soon. So we can use this clue to write a different implementation of our constructor that does a move, that sort of steals the guts of the source object because it's not likely to miss them for very long. We are going to do a shallow copy of the resource from the source object, and then just like we saw earlier, we are going to set the source object's resource to some empty state, so that when the source object is destroyed, it doesn't do anything. And by the way, this is why you want R value references to be non-const. You need to be able to write some empty state into the source. So we have basically stolen the resource out of this object, but it's okay because if we're in this constructor, it means the object we were called with is probably about to go away anyway. So this is what I was saying earlier. C++ gives us R value references and overload resolution, and we use those two tools to implement move semantics ourselves in our function overloads. Now there's this conspicuous no except here. In my opinion, your move constructor and move assignment operator are the only time when no except is really worth worrying about, but you should definitely try to make your move operations no except if at all possible. Here's something to Google for more on that. I won't dwell much more on it here. So now we've seen how these constructors are implemented. Let's take a look at a usage site to get a feel for it. So here we initialize some s with the result of a function, and then we construct a new s from that. This is going to call the copy constructor of s because we're passing in an L value reference. But if we cast it to an R value reference, now we call the R value reference overload. Of course, we could also spell that instead move. So what is the state of s after we construct s2 with an R value reference? Well, we know we wrote some empty state into s, but s is going to be alive until the end of the scope it was declared in. It's still there, it just had its resource stolen. So can we reason about it in any robust way? Well, for an arbitrary type, no. You could, of course, write arbitrary code in the move constructor that does whatever, and there's no controlling against that. But well-behaved types, including types from the standard library, follow this rule. A moved from object is in a valid state, In other words, all of its invariants still hold. It's not using one of those illegal bit patterns, but what state it's in is unknown. Now, this valid but unspecified state is notorious when you're talking about move semantics, but we actually deal with values in this state all the time. For example, at the top of this block, s is in a valid but unspecified state. We don't know what kind of s this function returned to us, but we can reasonably assume it's a valid string. We can use it however we can use any old string. The same is true for standard library types after you move from them. You can use them in any way that doesn't have any extra preconditions. We can ask for this string size. We can call cstr. That doesn't have any preconditions. If we want to do something that does have preconditions, we can check them first. So a move from string is still a fully baked string. But by moving it, we lose all knowledge about what state it's in. And if we want to use it further, we need to reestablish that knowledge. Now, I really like this idea because I like the idea that all of my values in my program are valid. But it means that if I want move to be efficient, probably implemented as stealing the meaningful guts of my type, I probably have to weaken my invariance of my type to include a state that is empty, just like we saw with the owning pointer earlier. For string, it makes sense because the empty string is a bona fide value of type string. But for many types like my s, what does it mean to not have my expensive resource? So wanting our types to be in valid states after move weakens our invariance. But also, valid but unspecified states don't necessarily compose. And that becomes clear if we take a look at a commonly touted C++ best practice, the rule of zero. The idea behind the rule of zero is that there are certain lower level types like vectors and strings and file handles and smart pointers that manage a resource. Those types should be RAII types. In other words, they should release the resource in their destructor. And once you implement a destructor, you probably also need to implement all the other special member functions for correctness. This is called the rule of 5, and your resource management classes should follow it. All your other classes, like your actual business logic classes, should be composed out of rule of 5 types, and they themselves should follow the rule of 0. In other words, they should let the compiler automatically generate the special member functions. See, this important business class has members that are rule of 5 types, but it itself doesn't declare any special member functions. Because it doesn't declare them itself, the compiler steps in and writes them for you. A compiler-generated move constructor looks like this, for example. It move constructs each member with the corresponding member from the source object. Each of those constructors leaves the member from the source object in a valid but unspecified state. But just because all of our members are themselves in a valid state according to what type they are, that does not mean that our class is in a valid state. Let's look at a concrete example of that. Here's cstring, which is an example I've also used in previous videos. It owns a null terminated character buffer and keeps track of the length and whether the buffer is all ASCII. Notice the invariants here. Len and isASCII both need to actually tell the truth about the contents of the buffer. To make things interesting, let's add a conversion to string view, where we initialize it with our pointer to our buffer and our length. Now, we haven't defined any move operations, so the compiler is going to generate ours. What it's going to do is move from each member of the source. It's going to move the unique pointer into ours. It's going to move the int and the bool, which don't do anything special when you initialize them with our values, so those are just copies. But the unique pointer is special. In fact, the standard library strengthens the policy for unique pointer. A move from unique pointer is guaranteed to be null. So after these two moves, the source object is in a completely broken state. It has a null pointer to its buffer, but its len member is still the old value. So if we tried to convert the source cstring into a string view, it would completely explode. So it's not enough that each individual member we have is in a valid state, because our type has invariants about the relationship between members, and those relationships are destroyed by this compiler-generated move constructor. And so I strengthen this statement at the bottom. If you have non-trivial invariants, especially relationships between your members, and you follow the rule of 0, your type will probably be in an invalid state after you move. Now, I've never tried this at scale, but I've had the idea of writing a helper template that's a rule of 5 type that holds a value and then uses the second template parameter as the moved from state. So that would mean our len would correctly become 0 when moving from it, which helps, but our pointer is still null. And you're actually not allowed to construct a string view from null, even if you pass a length of 0. So after move, we're still in an invalid state here where our public API can't be used safely. And aside from that technicality, it just breaks our invariant that our unique pointer is supposed to be pointing to a null terminated buffer. So this compiler generated move constructor just isn't going to work because it leaves the move from C-string in an invalid state. So we have to write one by hand. Let's try that out. So we'll start the same way as the compiler generated one. We'll move each member off the source value. Now the new C-string that we're constructing is in the correct state. But now in these curly braces, we need to reestablish the invariance of the C-string we just moved out of so that it's in a valid state after move. So we need to be pointing to a null terminated buffer. I guess we allocate one here, and then we update our other members to correctly describe the empty string we just allocated. By the way, I can't decide if the empty string is ASCII or not. Let me know what you think. And so this is simple and it sort of works, but this memory allocation means our move constructor can't be no except because allocating memory can throw an exception. Like I said earlier, we really want our move constructor to be no except. I also just don't want to allocate memory in here at all because that's expensive and our move constructor is supposed to be fast. Like that's the whole point. So what else can we do? Well, what if we just set aside a global buffer that we can use for the empty string? Well, that sort of works, but then we're going to run into trouble with our unique pointer, which thinks it's supposed to delete the buffer it's pointing to. So maybe we have to not use unique pointer and or add some conditional logic to our destructor to check for this case and not actually delete what we're pointing at. So that adds implementation complexity and means we can't use unique pointer, even though this is like what unique pointer is for, managing an allocation you own. We could also way increase our implementation complexity by doing something like the short string optimization, where we use some of our stack footprint to store characters inline when we're under a certain size. That's doable, maybe even desirable, but it takes this simple class and turns it into a full-on engineering project. I didn't even know this before I started working on this video, but this exact example of a simple C-string class appears in the original paper for move semantics. The authors there come to a similar conclusion as us. We have a few options here. Either accept that move from C strings will be invalid because our rule of zero compiler generated move constructor just completely thrashes our class's invariants. We could allocate memory in the move constructor or make the class significantly more complicated to support a no-throw move. All of these options are pretty unattractive to me, and they all stem from the fact that there's an object left behind after move that we need to worry about at all. If the object just completely went away after move, we wouldn't have to worry about reestablishing its valid state. Non-destructive moves are in direct conflict with strong invariance, performance, and simplicity. Now I want to look at another example of a real type in a well-known and popular codebase that has a noble goal of having a very strong invariant, but its parade gets rained on by this conflict between that strong invariant and move semantics. So I'm in the video game industry, and I've done some work with Unreal Engine. Unreal has its own implementations of a lot of things from the C++ standard library, and one reason is so that it can freely add non-standard extensions that it wants. For example, the Unreal implementation of optional, as of Unreal 5.4, actually does the thing I was talking about earlier, where it allows you to say, hey, here's a bit representation that is illegal for my type because of its invariance, so I don't need it. So you can use it to mean an empty optional, and that lets T optional here work on your type with no additional space overhead. Another thing Unreal provides is its own version of the standard smart pointer library. It has types like T unique pointer. By the way, the Unreal naming convention is to start the names of all class templates with a capital T. So T unique pointer corresponds to the standard unique pointer with very few differences. These both correspond to option box from Rust. It's an option because Rust's box can never be null, but these unique pointers can. So to match that in Rust, we weaken that non-null invariant by explicitly and externally wrapping the box in a layer of nullability using option. But Unreal wants to play this non-null game too. They provide an alternative to unique pointer called unique obj, which is basically a unique pointer that is always non-null. This is the equivalent of plain box from Rust. The C++ standard library doesn't have anything like this, although there are a couple of closely related library components that have been proposed. You should read about these if you're interested. One of the tricky things to figure out about their design is what to do about moves. Unique obj from Unreal has significant challenges with moves too, but we won't dive into those because unique obj isn't actually super widely used, and I have a different type I want to pick on instead in a moment. So following suit with the smart pointers we know and love, Unreal also provides an implementation of shared pointer. By default, this is just like std shared pointer or option arc from Rust, The reference count is atomic by default, although you can actually specify as a template parameter that you'd prefer a non-atomic reference count if you don't need to send these between threads, since a non-atomic reference count is less expensive. There's no standard library smart pointer that gives you a non-atomic reference count, but Rust has one called RC as opposed to arc, which is atomic. And rounding out this smart pointer library is a type that I very much like, more than shared pointer anyway. It's called shared ref, and kind of like unique obj, it's a shared pointer that is never null. There's no standard library equivalent, but in Rust, it's a bit like plain arc, no option. So let's see what this type is all about. It's designed to interoperate with shared pointer wherever possible, but provide stronger guarantees where they're available. So if I have a shared ref called ref, I can implicitly convert that to a shared pointer. This makes sense from a type system perspective. It's not literally implemented this way, but you can think of shared ref as a subtype of shared pointer, because all shared refs are valid shared pointers, but not all shared pointers are valid shared refs, because they might be null. So converting from shared ref to shared pointer is sort of an upcast. It goes from a more constrained type to a less constrained type, a stronger invariant to a weaker invariant, so it can safely be done implicitly. The other direction is not safe in general. It's a downcast, so it has to be done explicitly, and because it goes from a weaker guarantee to a stronger guarantee, it's possible for it to go wrong. So there's an assertion in here that will fire if you try to turn a shared pointer that's currently null into a shared ref. Doesn't work. Another thing I think is cool is that Unreal's make shared actually returns a shared ref. Unreal's like, we just allocated this. We know we have one. We know it's not null. So I'll give you back a type with a strong guarantee about that. Of course, it's kind of ignoring that allocations can fail, such is life. But you'll often see code like this, and you might write this, especially if you're used to the standard library where make shared returns a nullable pointer. This is fine. This just works because the shared ref returned by make shared gets implicitly converted to a shared pointer for you. Let's think about this in light of moves, though. First of all, I want to point out that especially if you're using atomic reference counting, you do want to avoid copying reference counted pointers around. Here's an oversimplified diagram of shared pointer. You can see it's pointing to some ref count, and when we make a copy, we have to increment that ref count. And then if we're just going to throw the source object away, we have to decrement that ref count. So we just pointlessly incremented and then decremented our ref count. This is not only some atomic operations, but it could be a cache miss when dereferencing the pointer to the control block that holds the ref count. So it's much better if we can just transfer the ref count using move. That way we never have to visit the control block at all. But the question, as always, is what to do with the old value. For a nullable shared pointer, we can just set the old value to null. But shared ref can't be null. So what do? Well, the Unreal Engine source code is freely available. So let's take a look. First of all, when you look at shared ref, you'll see a comment like this. It's not in the documentation. It's actually just inside the class body like this. It says shared ref has no default constructor, and you must initialize your shared ref to a valid object at construction time. Now, it shouldn't surprise you to hear that I love this. I love that they force you to establish a valid object so you don't have shared refs lying around that are half-baked. Unfortunately, if you scroll down a bit, you'll see there actually is a default constructor that's publicly accessible. It has a comment that says, don't use it. I can only imagine that the big block comment is older and represents their intention. They later made the painful decision to add a default constructor when they were facing some difficult problem. They either forgot to update the comment or they just left it there because it's where their hearts are. Anyway, don't use this constructor. Moving on. Shared ref has the expected copy constructor and copy assignment operator, which will increment the reference count of the object we're pointing to. No surprises. Now, what about our move operations? Well, they've done something clever for move assignment. With move assignment, you have two values to work with, two values that already exist in a valid state. So in order to efficiently move the source into the destination, they just swap the internal pointers between source and destination. They don't have to update any reference counts. The destination now points at what the source was pointing to, which is what we want assignment to do. And the source fulfills the postcondition of being in a valid but unspecified state. It's pointing to something else now, whatever the destination was pointing to before the assignment. So that's clever and is more efficient than copy assignment. But move construction. There's nothing clever to do here because we only have one value to work with, the source, and we have to leave the source in a valid state, which is non-null. So we have to just copy the source and increase our ref count. Unreal provides this move constructor just for completeness, but all it does is copy, and there's a comment in it explaining why. Seriously, go look at the comments in this code. They were thinking about this stuff. And inside this function body, they explicitly acknowledge that move construction takes a hit here because of the strong invariant of shared ref. On a similar note, let's look at shared pointer and its conversions to and from shared ref. It has an implicit converting constructor from a const reference to shared ref, and in there's another comment explaining again why there's no R-value reference overload, because we can't break shared ref's invariant. On the other hand, when converting to a shared ref, shared pointer can be smart. It has a const ref qualified overload of the conversion that will bump the reference count and give you a new shared ref. But there's also an R value qualified overload that moves the reference count into a new shared ref, leaving this null. And shared pointer can do that precisely because of its weaker invariant. So you can see how there's this direct tension between non-destructive moves and strong invariants. Let's go back and reason through this code. First of all, we're accidentally using that default constructor we weren't supposed to use. This is one reason why it's not super effective to leave a comment saying not to use a default constructor, because the language calls default constructors for you a lot of the time. On the next line, we are copying our shared ref into our shared pointer, so we increase our ref count. On the next line, we convert our pointer back to shared ref. This calls the const ref qualified version of toSharedRef. But we can call the R-value ref qualified version by moving the pointer before calling the method. Move temp is Unreal's version of std_move. It's basically the same, except it static asserts that you aren't trying to move from const, which I actually think is a nice feature. Anytime I'm trying to move from const when I'm not in generic code, it's a mistake. So it's nice to be alerted about it. Anyway, so we get a nice move here. Can't we just go up a couple lines and get a move here too? Well, no. Remember that wrapping ref in a call to move just casts it to an R value, which would just encourage overload resolution to prefer an R value reference constructor, but there is no shared pointer converting constructor that takes an R value, so it still just falls back to the const L value reference constructor. So copy is the best we can do here. Our first make shared is fine. We're creating a shared ref. Our next one is a little unfortunate. Initializing a shared pointer with the shared ref that is returned by make shared calls that copy converting constructor. So we get an unnecessary increment of our ref count when we assign the temporary shared ref into the shared pointer, and then a decrement at the semicolon when the temporary shared ref is destroyed. So this very commonplace looking code does something sort of inefficient every single time. And it's all because we have to maintain the invariant of this value that's about to blip out of existence anyway. Contrast this with the same situation in Rust. We have a non-null reference counted pointer, and we can easily just move it somewhere else. Because once we move out of the old value, it's gone. There's no invariant we have to keep upholding because no one is ever going to look at that value again, including its own destructor, which will never run. There's not even that much to say about this code, except that it's really simple. There's no unnecessary reference count manipulation, despite the strong non-null invariant here with arc. That's because destructive moves work with strong invariants, whereas non-destructive moves work against them. This tension appears in the standard library too. For example, here's a type with a very strong invariant. This is scoped lock, which is a newer version of lock guard, which you might also know about. The invariant is very simple. While a scoped lock exists, a mutex is locked. So we just know beyond a shadow of a doubt that while we are in this scope, we are holding the lock. Scoped lock accomplishes this by just completely disabling copy, which by default also disables move. So your scoped lock is nailed down to wherever you first create it. There's no way to transfer the holding of this lock to another scope. Instead, if we want to move where we're holding the lock, there's another type called unique lock that does support move. But look what else it supports. It also supports unlocking. So this type has a weaker invariant than scoped lock. When you have a unique lock, you may or may not have a mutex locked. So there's more complexity when you reason about this type, and there's a shadow of a doubt when you see one in your code about what state it's in. Now, I wasn't there when they designed this, but I suspect that what happened is that in order to support move semantics, they needed unique lock to have an empty state, so that a moved from unique lock would be in a valid state. So they had to add unlocked to the possible valid states that a unique lock could be in. Once they did that, they decided they might as well just let the user manually put it into that state too by explicitly calling unlock. And the result is a type that's not really a lock. When you see a unique lock, you may or may not have a lock. It's like an optional lock. And the tragedy here is that we already can express an optional lock like this. We wrap this simple type with a strong invariant in a wrapper, optional, that explicitly weakens its invariant on this one axis. Now to unlock, we just destroy the scope lock that's inside the optional. And to lock it again, we reconstruct the scope lock inside the optional. So we already have the tools to express this, but this type still can't be moved, because moving a std optional requires being able to move the inner type, which we can't do. So in order to support move, we can't wrap an empty state around our strong invariant. We have to intrusively build an empty state into our types, which makes their invariants weaker and more complex. Here are a bunch of types off the top of my head from the standard library that have an empty state built in. In all these cases, we don't really have a thing. We have an optional thing. But the optional is built into the type in a way that we can't strip off. That means we can't do the thing from the beginning of this video. We check for null once and then strip off that layer of uncertainty by using a type with a stronger invariant. If our API needs a std function instead of a pointer, there's no way to encode in the type system whether this std function is allowed to be empty. We just have to check or assert, or just cross our fingers and run the risk of a bad function call exception. By the way, that means the compiler has to generate code for throwing that exception if it can't prove that you already checked for null somewhere earlier in the call hierarchy. If there was a function type that couldn't possibly be null, you wouldn't worry about it. The compiler wouldn't either. Weaker invariants systemically harm local reasoning, which hurts your code gen, not to mention your own ability to be sure that what you're doing is correct. Notice I'm not saying, oops, this is bad because maybe we're going to pass a moved from object in here, to which you could just reply, well, don't do that and run a static analyzer and all that stuff. I'm not saying that. I'm saying that needing to support a valid moved from state has infected the design of this class and opened up that empty state as just a valid state that all std functions could be in. And it has a ripple effect throughout every use of std function, even the ones that aren't moved from. There is a push in the C++ committee, led by Sean Parent and others, to weaken this guarantee, to make it so that moved from objects aren't necessarily in a valid state. They're just in a state where you can destroy or reassign them. This mitigates the issue a bit. While I don't love the idea that that means that a move from std function is radioactive and possibly invalid, it would at least mean, hypothetically, that I don't need to guard against empty functions in arbitrary APIs, because I would know that a valid std function is not empty. If the caller passes me an empty one, that means they are definitely doing a use after move, and that's their problem, not mine. Std function itself would still need to support an empty state internally somehow, just for the moved from case, which is still unfortunate, but at least that weakened invariant doesn't infect your whole program, just the places where you've moved a function. So one last thing I want to mention here before we wrap up. We've talked about destructive moves, where Rust just mem copies your value and then doesn't run the destructor on the old memory location. Now, this is C++, where we're supposed to have the power to open up the hood anytime we want. So can we not just do this ourselves somehow? Can we implement destructive moves on our end? Well, if you try to do this with variables with automatic storage duration, like local variables on the stack, you're going to run into friction because the language calls your constructors and destructors in a way that's hardwired. I'm not going to say it's impossible to do something very cursed to get something like destructive moves for stack variables, but I discourage you from trying. But what if you're writing some code that manually manages memory, such as a data structure like a vector? In that case, you're probably manually invoking constructors and destructors anyway through placement new and placement delete. So in that case, you could definitely try to do this. It wouldn't save you from the weaker invariant stuff because your type would still need a traditional move constructor for things like stack variables, like I just said. But it could save you from having to actually move your objects around between your vector buffers, for example, which entails writing empty state into the source objects and then calling their destructors, which you know isn't going to do anything if they're moved from, so it's a waste of time. So this can be a valuable optimization to try to exploit. In the C++ world, this memcopy and forget thing is known as relocation, and a type where you can safely move it with a memcopy and forget is called trivially relocatable. It turns out that the vast majority of types actually are trivially relocatable. The only time when you can't do it is if your type's address is part of its state. In other words, if its location in memory appears in its bit representation in some way. This can happen if you have a pointer back to yourself, whether directly or indirectly. In this case, if your address changes, you need to update the pointer to point to your new location. In other words, update your bit representation to reflect the new address. So just memcopying will leave your value in an invalid state. But again, most types don't have this problem, so they're safe to relocate. You can imagine a vector implementation taking advantage of this. Now, the standard library vector does not. There has been some work done in the committee to try to get some version of relocatability standardized so that vector can take advantage of it, but for now, it doesn't. But other vector implementations do. For example, fbvector from Meta treats its data as trivially relocatable and gets some nice performance gains out of that. In fact, when you first plug in your type to fbvector, it will fail a static assertion. You actually have to specialize a type trait in order to say, I understand that my type needs to be trivially relocatable to work with fbvector, and I promise that it is. So you have to specifically sign off on this behavior before fbvector will agree to work with your type. On the other hand, tarray, which is the vector from Unreal Engine, just does this always without asking you. They're betting on your type being trivially relocatable, since most types are, and if you happen to try to use tarray with a type that is not trivially relocatable, you will spend your day debugging some weird stuff. You can ask me how I know that. But it's interesting how these pieces fit together, isn't it? Picture a tarray of tshared ref. Remember, tshared ref doesn't have traditional move operations because it doesn't have a valid empty state, but it is trivially relocatable because it doesn't have any pointers back to itself. So a tarray of tshared ref gets to magically move the shared refs around when it needs to without any unnecessary reference count manipulation. The strong invariant of tshared ref is not in conflict with destructive moves, only with non-destructive moves. So this is where I'll leave this discussion for today. I want destructive moves in C++ so that I can write simple code with strong invariants and get the best performance possible. I'm looking forward to hearing your thoughts in the comments. Let me know if you agree or disagree. And as always, I really appreciate you watching. I hope I see you in the next one, and take care until then.